In this video, we're going to work on moving our understanding of the atom from the Bohr model to the quantum mechanical, or the modern atomic theory. So where we left off with was the Bohr model of the atom. And what that stated is that electrons exist in stable orbits, that those specific orbitals we could number n equals 1, 2, 3, 4, and they were essentially provided different shells. Then we knew that electrons could gain or lose electrons as they transition between the orbitals, and that's what helped us to be able to explain atomic spectra and the absorptions and emissions that we would see there. This model also allowed us to be able to explain the Rydberg equation and where that came from, and those things made it relatively quickly accepted because, again, it explained these otherwise unexplainable pieces. But this model still had some issues. One of the major things is that it couldn't explain why only certain orbits existed, right? That from quantum mechanics or from classical mechanics, if we have a negative charge going around a positive charge, it should slowly spiral in towards the center, but we knew that that wasn't happening with these atoms. So we needed a little bit more to move forward. So our next contributor was de Broglie. And really the contribution here was the recognition that our electron acts both as a particle and a wave. And so what that means is that the electron actually had to complete an intact standing wave, if it's going to be a wave. And what we mean by that is just like a guitar string, right? We can have certain possibilities. If we have the string stuck on these two ends, we can have any number of whole waves that could actually be formed. Okay, but we can't have a partial one. We can't have this end where it's not at this point. So certain ones are allowed and certain ones are not. That same idea applies then to atoms. And the idea here is that, hey, when that n equals 1, we're actually doing one wave. If n equals 2, we're doing two waves. If n equals 3, we're doing 3, 4, etc. And that then can justify why we'd have these unique and distinct orbitals that are possible. That not just any orbital could exist, but only certain ones. And that's the reason then that we can't have sort of 3.5, for example, because we wouldn't be completing a whole number of waves. So this actually sort of enhanced the understanding of why Bohr's model might actually make some sense. The next contribution that we have comes from Heisenberg. And what he showed is that it's impossible to know perfectly both position and momentum of a particle. Now, this is relevant for our electron, right? Because if we're thinking about the de Broglie idea where we have these waves, as that electron's going around, if we know its momentum, we should be able to predict its position at any later point in time, right? Because it's just kind of going around in a circle. But what he showed is that our uncertainty in the position times the uncertainty in the momentum has to be greater than some value. Well, it turns out this ends up being relatively important when we have particularly small particles, such as electrons, and they're moving particularly fast, such as what electrons do. And so this gives us the idea that, okay, well, this, while maybe true for everything, is really most relevant if we have these sort of small things, such as electrons, that we're dealing with. And this also sort of reflects that wave-particle duality, that uncertainty in position reflects the particle nature of the electron, and that uncertainty in momentum actually reflects the wave-particle of the electron. So Schrödinger actually then sort of built on the ideas of Bohr, Heisenberg, and de Broglie, and then proposed the quantum mechanical model, which is what we still work with today. It had a couple kind of posits. What he said is that electrons are described by a wave function that determines its energy. And again, if we take the idea that electrons actually are both wave and particle, this is something that then can make some sense. In actually solving for these, what we find that only specific values of psi, that's this wave function, are actually possible. And if we take that wave function, we square it, that gives us a probability function. And what that means is that's where it tells us how likely an electron is to be at any particular location. And from there, we can actually come up with an image or a picture of where we think an electron would be most of the time. If we actually go through and do this, it turns out that we get 3 quantum numbers, 3 restrictions on what things can be. Now, you're not going to have to worry about the specifics of this too much. If you're really interested in the math behind it, you can either look it up or take some more chemistry classes. You'll get into it in quantum mechanics. It's very interesting, but it's a little bit beyond what we want to focus on here. Instead, we're going to sort of focus more on what are the outcomes of these quantum numbers, what are the outcomes of these restrictions. And so from the quantum numbers, we actually get information about the orbitals. And when we're considering the orbitals, we often really want to think about their relative energy. So we're going to put these on an energy scale, right? Lowest energy at the bottom, higher energy at the top. And from the very first quantum number that we get those same shells that we saw with the Bohr model. So we can have values of 1, 2, 3, 4, and those give us different shells. Again, essentially, on average, how far away are the electrons from the nucleus. We do get a second quantum number, though, and that leads to subshells. So we don't just have these individual 4 shells, but it turns out within those we actually separate them just a little bit. And each shell gains 1 new subshell, as it turns out. So the first shell only has 1 subshell, the second one has 2, the third one has 3, the fourth one has 4, etc. And they start to, when they break them apart, the energies vary just a little bit. These actually have different names. You might have seen these before. If you had a high school chemistry class, you might have talked about it. The first subshell in any shell is an s orbital or an s subshell. The second one is a p. The third one is d. So if you recognize those letters s, p, d, f, that's what it's talking about. It's talking about the subshells. The third quantum number actually tells us the number of orbitals that exist in any given subshell. And so we can break those up into individual pieces. So an s subshell, as it turns out, is always going to have just 1 orbital. A p subshell is going to have 3 orbitals, a d is going to have 5 orbitals, and an f is going to have 7. Again, that's sort of just how the math ends up working out when we do this quantum mechanical model. And the subshell actually gives us more information that's really relevant, and this is where it starts to become more useful for us in some ways. So again, we said we could take that psi squared, which would give us a depiction. So for our s orbitals, we end up with a spherical shape that the electron is likely to be in. And this comes up and we make these drawings. And what that means is that 80% of the time we would expect the electron to be within that particular zone. That means there's sometimes that it would be a little bit further out, further away from the nucleus. And anytime we have an s subshell, it's always going to have this spherical shape. But there still are differences. If we think about a 1s versus a 2s versus a 3s, the piece that gets different is actually the size. So the 1s is a little bit smaller, it's closer in. The 2s is a little bit larger. The 3s is a little bit larger yet. Okay, and so the larger that shell, again, the bigger the size. So again, this is consistent with what we were thinking about when we talked about the Bohr model. If we then talk about our p subshell, these have a different shape. So there are, first of all, we said there were 3 of them. So we can see that there are 3 different depictions here. These have essentially a dumbbell shape. So we've got 2 different lobes to it. And these 3 orbitals are lying perpendicular to each other. So they have names of the px, py, and pz because these lay and have an axis along the x, the y, and the z axis here. And so again, we're trying to depict that these things are perpendicular to each other. One of the other things that you notice about this is that we have 2 different shadings. This is very common and it's relatively important as we sort of think about it as we use them a little bit further on. And what these shadings actually represent is what we call phases. We don't have to worry about it too much in the class, but the basic idea that I find to be really useful to sort of remember is that, remember, this is psi squared. So just like if we take a number and squared, whether we start with a positive or a negative, we get to something that's positive after we square. Same sort of idea here, that essentially these phases we can think of as being sort of a positive side and a negative side. Again, that has some utility later on when we talk more about these. What that means is if we're going from a positive to a negative, right down the middle here we have a 0. So there is actually what we call a nodal plane. So there's no possibility that the electron can be along this particular plane. But at one time it could be over here, a little bit later it could be over here. One of the things that sort of messes with our mind just a little bit, if we think about in a very macroscopic sense, is that we know that the electron can never exist along that nodal plane, but it goes from one side to the other. Again, quantum mechanics has some weird things. That's just sort of a small taste of where it starts. We can then consider the third kind of subshell, or those d orbitals. The d orbitals, what we see is that most of them have this clover shape, these first 4. Again, those lobes will alternate their phases from positive to negative with those 2 nodal planes that sort of split them. The names here, the dxy, this shows the plane that it's lying along. The xz shows that it's in the xz plane, etc. This one that has this slightly more unusual name, here it actually lies along those lobes lie along the axes, so it's just a little bit different. This last one, the dz squared, is just a little bit more different. It has a little bit of a dumbbell shape with sort of a torus around it. Again, we're not going to worry too much about that, but it's nice to know what the different pieces are. And we'll see some places later on where the shapes of these orbitals will have potentially an impact on bonding. If you're really interested in sort of shapes of orbitals, here's a free viewer that you can download and you can kind of play with just a little bit. Okay, so this gets us to one more idea. This is the Pauli exclusion principle. It says that no two electrons can actually have the same set of quantum numbers. Okay, that seems like that's something that is reasonable. We know it takes 3 quantum numbers to describe an orbital. Okay, that's cool. But we also know that there are 2 electrons that can fit in per orbital, so that actually gives us a 4th quantum number, as it turns out. And the way that this comes about is that an electron will actually spin, and when we have a spinning charge, that creates a magnetic field, and we see that we can actually end up with electrons that are either spinning in an upward direction or a downward direction. And so those 2 different pieces end up being our different quantum numbers, or our spin. Okay, so let's just see if we can kind of pull all this together just a little bit here. So again, we have that energy diagram that we have for our different orbitals. We have the names of our subshells. So we have a 1s, a 2s, a 2p, etc. And then we can think about, well, how many electrons can we actually put in there? So again, we know that we can have 2 electrons in any one orbital. So if we think we only have 1 orbital here, okay, but we can put 2 electrons in there, well, then we can get 2 electrons in a 1s shell. The 2s, again, we have 1 orbital there, 2 electrons go into each one, so there we can have 2 electrons in there. So for any s subshell, we're always going to have 2 electrons. If we consider a p subshell, we've got 1, 2, 3 different orbitals there. So each one can hold 2 electrons. That's going to be a total of 6 electrons. So what we'll see is, again, that'll hold true for the 3p and the 4p as well. If we get to that d subshell up here, we've got 5 orbitals. We think 2 electrons per. Okay, that should get us to 10 electrons. Again, and that's going to hold true for the 4d as well, and then the 4f, similarly, we get to 14. So that gives you a little bit of sense. Okay, how many electrons can I put into each one of these subshells? How do I actually remember all this? That's a good question. Well, it turns out it's really easy, actually. So we're often interested in sort of what is the order of these things, how would we fill them? Because we know that if we start putting electrons in here, the electrons are going to go to the lowest energy scenario, so we'll start filling this one first and then fill up. And so what that means is that we can actually use the periodic table as our crib sheet for this. So the order that the orbitals will actually fill, we can see in the periodic table. So I shouldn't necessarily say it's determined by, but we can get it from the periodic table. So the first electrons that we see are going into the 1s, and then the next ones are going to go into the 2s. The next electrons that we have are going to go into the 2p, then the 3s. And so we can start to use the periodic table to see the order that these things come from. So as we go across and fill these things out, you see the order that they fill. So what that means is you don't actually have to memorize the order. So that's really good. We can just grab the periodic table and we can see the relative energy levels and how they fill. So that's really cool. So then one last little piece here. That when we look at the S block here, that's what we call this, because these are all filling in the S shell, have their outermost electron in the S shell. So in this S block, the number for the shell is the same as the row number. So we'd think 1, 2, 3, 4, 5, 6, 7 down the row. The same is true over here for the P block. So for the P block, what we see is this row is the 2p. Remember, the second shell is the first time that we have p orbitals, and then we start filling each one in subsequently. And so there's a second row, third row, fourth row, etc. When we get to over here, we want to keep in mind the first shell that we actually have, where we have d's, is in the first shell that we have, the d subshell, is in the third. So these first d's that we're filling are going to be the 3d's, even though, note, we fill the 4s before the 3d's. Okay, so something to pay attention to. And then each one obviously is subsequent. So if you're paying attention to row number, this is 1 behind. So we take the row number, we minus 1 to figure out what shell we're actually filling. Down here, if we look at the f's, again, the first row of the f's, the first time we encounter those as a possibility is going to be in the fourth shell, right? Because they're the fourth kind of orbital that we have. So that hopefully will help you keep track of which number goes with which shell goes with which. So now if we step back and we sort of look at our key models of the atom, again, we went from Dalton's model. When we added in the knowledge of the electrons, that got us to that plum pudding model. Rutherford then moved us and advanced us towards the nuclear model. And then Bohr sort of adjusted that a little bit into the planetary model to be able to explain what we saw in terms of the atomic emission spectrum. And then with a couple additions, we actually get to the quantum mechanical, which is, again, the current model. And so one of the things to keep in mind is, obviously, we've seen quite a bit of change over time. And one of the things you might think about is, are we done? is it possible that there's still new things to discover about the atom that might change how we think about it?